I'm Andrew Durack and I'm the CEO and founder of Durack. Our mission is to develop revolutionary computing that will allow us to solve problems that even the most powerful computers today cannot. Standard silicon chips generate heat. We know this when we feel our phones or laptops getting hot. At the moment, most quantum computers need to be cooled down to really low temperatures, around minus 273 degrees. If they are much hotter than that, then the qubits stop working and the technology becomes useless. Dirac's breakthrough, just published in Nature, shows that we can operate spin-based quantum processors where the chip can get 10 times hotter and still remain accurate, making our quantum computers faster, smaller, and more environmentally friendly. So we're getting closer to building quantum computers that can solve globally significant problems that even the largest supercomputers would take millions of years to solve. Some examples include finding vaccines to new diseases much faster than can be done using modern medicine, or design new molecules that could take carbon out of the atmosphere to help us solve the world's climate challenges.
Recording in
Dirac's
progress.
technology will touch and transform every industry worldwide.
Hello everyone, welcome to another exciting episode of Xpert Insights, exclusively brought to you by Cynix Design. I'm Christine Gohar and I'll be your host for today's session. Whether you're joining us on Zoom or watching via Facebook Live, welcome. For those of you who are tuning in for the first time, Xpert Insights is our ongoing webinar series where we bring in industry leaders, experts, and innovators to discuss the latest trends in technology. We're all about learning, sharing knowledge, and exploring the future of tech together. Now, before we jump into today's exciting discussion, a few reminders for everyone. So, if you're on Zoom, please keep your microphones muted and your cameras off to minimize distractions. And if you get accidentally disconnected from the Zoom and upon trying to get back in, it's full, yeah, sorry about that. We're still begging for a bigger Zoom budget, but we are also live on Facebook, so you can tune in there too. And if you have questions, just send them in the Zoom chat or the Facebook Live comment section. We'll get to as many as we can during our Q&A session. So for those who are attending to receive a certificate, we'll be sharing an attendance form later, so keep an eye out for that and make sure to fill it out before the session ends. Alright, so let's get started. Today's topic is one that feels like science fiction, but is actually science fact. Quantum computing, a glimpse into the future of tech. We're about to dive into the world of superposition, qubits, and computing power beyond imagination. And guiding us through this mind-expanding topic is an incredible expert. So our guest today has an incredible background in integrated circuit layout design and quantum computing. With over 20 years of experience in chip design, he has worked with some of the biggest names in the semiconductor industry: Intel, GlobalFoundries, and TSMC, just to name a few. Currently, he's part of Dirac, a company working on developing the next generation of quantum computing hardware. His expertise spans everything from chip-level layout integration to the latest quantum computing technologies. Everyone, please join me in welcoming George Pagulayan. George, you there?
Yes, Christine, thank you. Thank you for that very warm introduction. And thank you for the whole Cynix team for doing this kind of webinar. And I would like to say thank you as well to the participants. Right now, I can see here like a 300 to 295 participants. And that's not counting those watching from live in Facebook. And as I heard last night, our total number of registrants are more than 1,000 already. And yeah, so that makes me feel more excited. And the reason why is because later on we'll be discussing about the power of exponentials. Just imagine those 1,000 registrants would talk to two people at the same time. Then this information would expand into like a number of 1 and then 300 more numbers next to 1. Just imagine those, how powerful that exponential is, right? So we'll tackle that exponential later on throughout the session. So hopefully everyone is excited to learn more. And just to set the expectation, I'm not here to give a lecture about quantum mechanics, not in an hour. We can do that. So I thought about just telling a story. So I have a 3-year-old son. That's what we do most of the time. I find it effective when you tell stories rather than giving instruction. So let's do that in this session, and hopefully you enjoy the stories that I'll be sharing with you. All right.
Yeah. Okay, George. We're thrilled to have you here today. I think I speak for everyone here, and we can actually get started. So why don't you take it away?
Sure. Let me share my screen then. All right. Sharing screen. Thumbs up if you can see the screen. Christine, can you see the main just for testing?
Yep.
Okay. All right. So, but before we start, as I've said, let's set some expectations. So, if I have one key takeaway that I would like you to get from this session is changing perspective. So we'll discuss a lot of new things or concepts that may be uncomfortable to take at first, right? So that's what I want to tell you. Just accept it, and later on, hopefully, it will change our perspective of seeing things around us. All right. So let me. And so before we start, I have these two person in front of me, Richard Feynman and Neil deGrasse Tyson, which are my heroes right now. The reason why is that Richard Feynman is a physicist, and Neil deGrasse Tyson is an astrophysicist. So they kind of give me the perspective of the two worlds, the bigger world out there, and then Richard Feynman, the small world that we'll be talking about, or the quantum world, right? So here's the quote. Try to absorb it for now, and understanding the knowledge about quantum mechanics, or at least the basics of quantum mechanics, because there's really a lot. This is something new to me personally, because my background is in IC electronics and communication. So I'm dealing much with electrons, numbers of electrons. But this one is up to the smallest particles that we'll be discussing, and it's hard at first to really accept the basic principles of quantum mechanics. But if you get to think about it, it's not really strange. It's not unusual. It's just the way we are right now. It's just how the nature is. And it took about 100 years before we have fully understood and we have fully accepted the explanations of our early scientists now that we are at this point. Okay. So always, I'll refer to you to these two quotes as we go along. And I prepared, I expect that a lot of us have watched or even read a lot about quantum mechanics, science, and physics. So it's really hard and really hard to absorb everything. So I tried to create this topic outline wherein part of my story would be discussing about some of the hypes and misconceptions, and then of course the fundamental principles of quantum mechanics. Now that we are actually, we are at the early 20s of year 2000, and we are right in front of a new frontier, if you may say, of this new revolution. So, and then let's try to get the idea of how to build a quantum computer, and after that, let's talk about what's next after knowing or learning something about quantum computing, right? Okay. So first is I see that we have a perfect timing for this kind of webinar because this year we are celebrating the International Year of Quantum Science and Technology. So actually UN working with a lot of scientists and science communities around the world have decided to declare 2025 as the International Year of Quantum Science and Technology with the sole purpose of really informing the public, telling the background, the concepts, principles behind quantum mechanics or quantum science in general. So there's a lot of countries all over the world, like 70 countries all over the world who have participated in this effort of informing the public. And DIRAC is a proud sponsor of this International Year of Quantum Science and Technology. Right? So it's 100 years, and I'll be showing you a picture. So the way we'll do it is, let's go back a little bit in history. Okay. So for some or most of us, I hope that this is a familiar photo. And why this photo is important is that you see here 29 great scientists. And I think the most familiar one for most of us is in the center, so Einstein. And the great thing about this is 17 out of these 29 scientists got a Nobel Prize for the things they did for science. So just imagine this is the modern, this is the old version of a podcast or a webinar where these great scientists are tackling about the difficult problems of science at that time. So early 1900s, 1927 to be exact, this is the 5th conference. But then this is very monumental because this is when we consider that the basics of quantum mechanics has been born, right? And just a little background as well for the people that you see in the picture. So everything started when we had the light bulb. So the light bulb was invented in 1879. Remember, this is early 1900s. So close to being 1900s, 1879, 21 years before the 1900s, there's already a light bulb by Thomas Alva Edison, right? So from there on, there's a lot of effort in trying to maximize and optimize the use of energy emitted by the light bulb. So Max Planck here, we know him for the Planck constant, was assigned to investigate and optimize that light bulb, right? And upon his study during exactly 1900, he was able to propose the idea, that's when the quantum theory started, the idea of that the light is emitted through a packet of energy. So that packet of energy is a quantized portion of that energy, right? And then right after Max Planck, 1900s, so 1905 comes Einstein, and he was able to propose or use Max Planck's idea of the quantized energy of light into his photoelectric effect. So that's his. He won a Nobel Prize for that one as well. Wherein the photoelectric effect is when you shine a light in a certain metals, they give off electrons or electric current. That's a fundamental knowledge that Einstein created in 1905. And then he was able to use Planck's constant in there. And then right after a couple of years, 1913, Niels Bohr here proposed the atomic model. So from there, if you can see it's starting to make noise in terms of the quantum theory at that time. And then if you remember, Niels Bohr is the one who created that atomic model. Later on, we'll discuss shortly about that as well. And then come a few years later, we have Heisenberg here. And then we have Schrödinger. So actually, when Schrödinger created his equation about the quantum state of physical system and worked with Heisenberg. Heisenberg is known for his uncertainty principle, wherein uncertainty principle says the speed and location of a particle, you can't measure that at the same time, right? So the practical use of that, if you would want to use it, is during driving, when a policeman tries to apprehend you in terms of overspeeding and ask you, do you know what your speed is? Then you can say, no, I don't, but I know my exact location. So that's, in a way, an old physics joke wherein uncertainty principle says you can't know exactly your speed and location at the same time. There's always this uncertainty. All right. So there's a lot more of scientists here who worked way back 1927 to create the basics of quantum mechanics. So just a perspective looking back, that's why we are celebrating the 100th year. It's some kind of close to 2025 or 1925. People and scientists are really serious about solving a lot of difficult science problems, right? The technology is not there before. There's a lot of theorems as well that cannot be proven during their time, wherein we have been able to prove as time went by by other some known scientists, right? So just always remember and take note of this great picture. It's a testament of a collaboration of the great minds in our history, right? And I'm showing here just to add more into the seriousness of the science and the problems that it's trying to solve, this Large Hadron Collider in Switzerland. So it's a 27-kilometer ring of superconducting magnets. It's underground, and the reason for this is the purpose of this LHC or collider is to measure the properties of all the particles available and known as of now. Application-wise, there's a lot of application, but what I want you to understand here, or like digest here, is how serious people are investing in this kind of studies. We are, as Christine mentioned a while ago, when we discuss about quantum mechanics, quantum science, it's like we are dealing with science fiction, but it's actually not. And these are the proof that what we're dealing with is real. So, and if you think about it as well, some of the Marvel movies, Quantum Mania, Parallel Universe, has some kind of a basis as well, right? So let's just absorb this for now, but I would like you to understand these are all serious. These are lots of billions of dollars investment all over the world. All right. So before we jump into a more complex discussion, let's define what really is a quantum computing. So let's digest the words quantum and computing. So quantum, from the Latin word quantus, meaning how much, like an amount of, like that's why we have the quantity. Okay? So this is the small what do you call it, measurement of any object or discrete unit. Computing is the process of any goal-oriented activity requiring or benefiting from or creating computer. So with this quantum computing is that process of or aspect of computer science, physics and mathematics, leveraging from the quantum mechanics principles, right? Let's address the main question. So what's the difference between a quantum computer? So from time to time, I'll jump from saying quantum computer, quantum computing, but basically we're referring to same aspects. So what's the difference between a quantum computer and a like a classical? For now, we're saying it is to be classical computing, and the difference when we say a supercomputer. So just think about quantum computer and a classical computer does the same thing for computation, right? But there are just some things that even a supercomputer cannot do, right? There are also things that or tasks or job that a quantum computer may not be worth doing, but is best used by if we can use classical computer. So in analogy, we can say that both quantum computer and the classical computer are kind of a transportation or mode, wherein we can say we use cars when we are driving on land, and we try to explore places, but we use boats when we explore the ocean or the seas. So it's really a different application. And it's because of the basic principle used by the quantum computing, which is the quantum mechanics, which we'll discuss later. All right. So I guess it'll be more effective to see the difference as well if we can demystify or debunk this some misconceptions here that quantum computers are a replacement for classical computers. Nope. As I just mentioned, they are two different things. They have their own, they are good at different purposes. And it's just that, no, we don't see the time that quantum computer will replace the classical computers. Okay. And then another one here is quantum computers are faster in all computational work. No. Quantum computers are best in works like simulations, machine learnings, building models, optimizing routes, right? Simple day-to-day work or tasks such as Word, watching video, there's no significant increase in speed if we are going to compare it, at least for now, right? So, and then we have this here, and I'm hoping or assuming that you have watched a lot of videos and researches already that quantum computer will end encryption. So no, actually, there's a lot of parallel efforts now ongoing wherein we are creating a quantum safe encryption protocols already. So if you're gonna think about it, the software side is ahead of the hardware side at this point. So we have the algorithms already because that we know the advantages of once the fully functional quantum computer is ready. We know, and everybody knows in the world of science, and even the governments know the dangers and the advantages of having this encryption. Yeah, it can take advantage of the quantum computers, but of course, I would like to believe there are more good guys than those hackers who are actually now preparing for that time when quantum computer is available that are we will have a quantum safe encryption decryption system. Right. So encryption, by the way, for decryption, this is a system that we use when we try to input our PIN numbers in banks, right? Your QR codes, what do you call that? Yeah, the QR codes or the numbers that you get. So those are the encryption decryption process that I'm talking about. Right. And then another one is quantum computer applications is science fiction. No. Just imagine right now that it sounds like science fiction, because if we go back in the history, we are at a stage right now wherein, like the classical computer was generated or developed, you can't imagine the applications that are going to be done. So now, coming from our basic computer before, now we have a lot of applications, apps, lots of machine learnings and AI applications as well. So who would have imagined that those who created our first computers will be able to use this powerful tool in what we have right now. So the way we communicate right now, through this, right, all over the world. So who would have imagined that? So, and then the last one would be quantum computers will only benefit governments and big private businesses. Actually, no. If you can think about it, many of the problems that can be solved with quantum computers or quantum computing are relevant to smaller businesses and organizations. It's just that right now, the effort of creating this takes a lot of needs and takes a lot of money, of budget. So that's why if you're going to search on the efforts done, the big companies are there: IBM, Google, INQ, and other companies. Later on, you'll see a list of those companies who are currently involved in creating this quantum computer. And on this side, you'll see like some differences, key differences of quantum computing. And for the first one, quantum computing deals with qubits. Later on, we'll discuss what qubit is. But the main difference to classical computing is that our classical computing deals with 1 and 0 only, like a switch that is either an on or an off. But in quantum computing, we have this third state, either a 0, an on, an off, or a 0 and 1 at the same time. So that's the key and basic difference of the two, which sets apart their functions and their applications. I mentioned about exponential a while ago. The power of computing in terms of quantum computer increases exponentially. So later on, we'll discuss about qubits, wherein if you just quick differentiations that for a simple bits, we only have either 1 and a 0, but we have 3 states for a qubit, right? So that already sets the difference into how much possible states we can play with if it is a quantum computer. And then, though quantum computers have high error rates, we have a solution for that. We have those fridges. We have to keep it ultra cold. We say to the temperature of near absolute zero. So absolute zero is a negative 273 degrees Celsius. So that's zero Kelvin, right? So just imagine how cold it is right now. If you're in a room of like an air-conditioned room, 16 degrees Celsius, you feel already cold. So imagine negative 273 degrees Celsius. How cold is that? Right? And I mentioned the fourth one, the task that can be handled by quantum computer and classical computer. All right, so now let's go to the fundamental principles. Okay, so this is when and where I want you to apply the first two codes that I showed you a while ago. This is something. This is something that may not acceptable, right? When the first time you need hear this, because we are actually um, like educated or raised in a bigger world. So it's hard for us to appreciate and accept how quantum really work. Quantum meaning the smallest, right? Smallest particles. Okay. So let's start with qubits. Qubits or quantum bits. And going back, bits is a shortcut as well of binary digits. So if you can recall, so it's just so funny that we are trying to incorporate a lot of making the words shorter as we move along. So quantum bits is the basic unit of information measurement of quantum computers, which, as I said, can be a 0, a 1, or a proportion of either 0 and 1. So that's what makes it powerful, because we can manipulate or play with those states in between 0 and 1, right? But take note that those 0 and 1 and the states in between them will end up either a 0 and 1 or 1 only if you make the measurement or observation. Just to give you a little bit of perspective in terms of what we're dealing with right now in terms of number. Look at these numbers right here. I'm showing here a light year. So a light year is the distance that light travels in 1 year. Okay. In terms of how far it is, it's 9.4 times 10 to the 12 kilometer. That alone, I can't process in my mind how far, how big it is. Let's round that to 10. The 9.4 is rounded to 10. So that means 10 times 10 to the 12. Imagine 10 million kilometers. And right now, our universe, it's expanding. Imagine how far is a 93 billion light years, right? So that's how powerful and how big of a number it is. And dealing with these big numbers in terms of computations can never be solved by the classical computer. Another one that everyone can relate with is file sizes, right? So let's start with terabyte, because I think this is what's more familiar right now. Terabyte means 1 terabyte means this number in terms of 1 unit of information in our binary measurement is 1 bit, right? So if you have a 1 kilobyte, that means you have 1024 bytes, right? And just imagine 1 terabyte. You have your hard drives, right? And hard disk like this big. Imagine 1 billion of that for 1 petabyte, right? So that's how big of a number it is. And later on, you'll see why this is important for the perspective that I'm saying. It's a large number, big number to deal with. And as I mentioned, I have this son. In appreciation for the big numbers, we actually celebrated his 100 million seconds of birth last year. So just to get that perspective of appreciation of, wow, 1 second. So you have been alive, and we're being happy for about 100 million seconds already. And if you want, for you who are attending here, if you want to do something different on your next birthday, you can celebrate your 1 billionth second of existence sometime when you are 30. So we can do the computations, but it's a good way of celebrating, just to have that appreciation of the big numbers, right? Now, there's a lot of efforts already with the different companies, and now if you can absorb it, the way we what do you call it, quantify the power of a quantum computer now is through the number of bits, right? So let's go back a little in here. The binary measurement shows us the number of bits that we can be playing with. When we have like a 2 to the 4, we have 1 and 1, 2, 3, 4, 12 numbers next to it. That's the number of states that our quantum computer can play around with. So that's why the race right now is, look at these numbers. So this was published October 2023. So it's too old for now. And looking at the latest news or latest progress we have, some are even claiming hundreds and to the million qubits already being, thousands of qubits already being developed. So you can visit the RAC site and see our roadmap there on how do we plan to contribute in terms of the number of qubits to be developed in the years to come, right? So you can see your 73 qubits for Google at that time, IBM 433, 2023 coming soon with IBM already targeting 100,000 qubits. So just imagine 2 to the 1,000 to the power of 1,000, how much data are we going to handle when the time comes, right? So we have 4 fundamental principles of quantum mechanics. We have the superposition, entanglement, interference, coherence, and decoherence. Showing here is the famous Schrodinger's cat. So, but in superposition, this is the unique ability of particles to exist in multiple states simultaneously. The catch is until they are measured. So this thought experiment of Schrodinger's cat. So the setup is that there's a cat placed in a box with a radioactive substance that if that radioactive substance decays, a mechanism will trigger to break a flask that has a poison, releasing the poison and then eventually killing the cat. Since this is a thought experiment, what we gain out of here is that if you're asked, is the cat alive or dead? The answer would be that, since a thought experiment, the answer would be he is both dead and alive until you open the box, right? So even Einstein and Schrodinger had a lot of discussions about this, and even Schrodinger himself was confused about when they were discussing about this, right? And on this side, just a little going back to the history, we have if you're familiar with the atomic model developed by Rutherford. So it's not really how the electrons works, and then come Niels Bohr, who proposed that electrons have their own certain locations based on the energy that they have, and then Schrodinger developed that model by proposing that this electron cloud model. So instead of treating electrons as particles with definite positions and velocities, quantum mechanics treated them as probability of waves spread around over a range of possible position. So this is driven by the principle that until you measure or observe a particle, he takes the property of a wave. Until you measure him, and then you will see him as a particle, right? So that's the explanation of a wave particle duality. And another principle that's what do you call it? Not to be unusual is the entanglement. So this is a phenomenon where the quantum states of two or more particles are interconnected. So this is not unusual. So every particle has their plus and sides, or the negative and positive electron, what do you call it? Protons, right? And we are made up of this entanglement. Our body is made of what? 60% water, and water is an entangled molecules of 2 hydrogen and 1 oxygen, right? So H2O. So it's not unusual, right? But then what it says here is that an entangled particle, even they are separated to distance, are cannot be described independently, but both of them, because each particle is represented by a wave, and then that wave or wave function is represented by mathematical equation combined with the other particles. So both of them together doesn't exist anymore, but of their wave function together. And later on, we'll see the spin. We'll talk about the spin, so a property of the particle, which for now we say up or down. Okay. Then we also have interference. Just imagine this: we have the double slit experiment, wherein you would have expect, if you have two slits, you would have expect that what you see on the other end would just be two patterns of light, right? But experiments, this is not a thought experiment, but an actual experiment that shows us that this pattern at the back was created. So that proves that the electrons, or the photons of light, is actually interacting with each other, creating that kind of taking the wave-like property that we see here. Okay, and then interference could be constructive and destructive. So when they combine, they take the peaks, and then they cancel out when during the destructive interference. Coherence is just the ability to retain those entanglement, or the superposition. And this is one of the most challenging problem that we have in designing qubits. Let me make it faster, because I think we are down to like 14 minutes. So hopefully you feel right now that you kind of feel uncomfortable hearing those kind of fundamentals, but that's a good indicator that you're getting it, right? So just go back and say the first two quotes that I got presented a while ago, that okay, it doesn't make sense, but yeah, the universe doesn't make doesn't have the obligation to make sense for us. We are the ones who have to make sense out of it, right? So let's cross the frontier. So now these are the companies. So it's new to me as well that there's a lot of companies already involved in this. I just went here to Australia like 2 years ago, and luckily landed on this job, and that's why I wanted to share what I see here, how it unfolds. So hopefully after this session, you'll have that knowledge that there's a lot of efforts already ongoing. Just go search, and there's a lot of companies out there who's involved in designing quantum computers. And I'll not go through this for the sake of time, 217. But the important thing here that I'm showing is there's a lot of different modalities or modes that qubits are being made. It's actually a design. It's not just a form of measurement, the qubit, as I mentioned. We are designing the qubits itself. Imagine the electrons. You are manipulating the electrons. It spins up and down to be read out is as either 1 or 0 based on the circuits that we are making. So we have superconducting, ion trap, neutral atom, and photonics. And in terms of approaches of the different companies, these are the companies who are using these different kinds of qubit manufacturing qubits. So Dirac is using the silicon spin, as I mentioned, or the quantum dots. We are designing. This is an actual design. This is what I do. This is what we do. So we are designing this. If you are not familiar, this is a transistor on a super microscopic nanometer level. So the ones you see here are actual connections. I have here like the sticks. Imagine those sticks. Those are actual metals right on top of each other. Wherein displaced in the middle, those representation of the qubit is like a well. It's like a well, a container wherein that's where you manipulate or contain your electron or your single electron. So this silicon spin works with a microwave antenna wherein you use that microwave antenna to manipulate the spin of the electron. So imagine it works like a radio. So you just tune into a specific frequency so that it's either you are up or you are down. That's how it works. And it's real. We're designing this. All right. This is same thing. SET is a single electron transistor. So we might not be familiar for now because we are used to getting working with the usual transistors. We have the base, the emitter, or the collector, or the source, drain, and gate type of configuration. But this is a big unusual type of transistor wherein we are manipulating one electron at a time, taking advantage of the spin up or spin down. Okay. Now let's try and building a quantum computer. So I hate to be the deliverer messenger of the bad news, but we are not having a quantum computer like we expect to be, like a laptop or something, and you'll understand why. At least for now. So what we see here is the minimum setup. So imagine this is a quantum computer. The whole setup is a quantum computer. The ones you see most of the time would be the fridge, this one right here. And then the chip is at the bottom of that. And this is a magnified version of that chip diagram here. In actual, this is how the lab or our office looks like. The left side is an IBM setup, wherein the fridge right here is a dilution fridge, wherein it can cool down up to 14 millikelvin, right? So the two pictures on the right side are from Dirac. This is our old office setup, and these are the measurements being done. So just imagine how expensive the setup is for right now. That's why I always say we are at a point of the vacuum tube stage when we were designing the early computers, right? And aside from those equipments and setups, the approach to really build a quantum computer, it would take a full stack approach of changing things. If you can see here, most of the things that we need, just remove all the quantum word. It's almost similar to the classical computer that we have, although of course we put the quantum because of the principles that are being used. It's based on the quantum mechanics. Challenges. Number one, qubit quality. Quality means it's hard to compute for to control the qubit because electrons keep on spinning. That's why we have that cold fridge, the dilution fridge, because the lower the temperature, the less the electron moves. So the more that you can control the movement of the electron, putting it either spin up or spin down, would he give you the desired output. So that's why it's hard. It's a challenge right now, but it's improving. Qubit scalability. So how do we go from 50 qubit to 100 to 1,000 or even a million? That's one of the challenges. Hardware limitations. Aside from the ones that I've shown you, there's also a lot of manufacturing, and even foundries are having a hard time right now. We don't have PDKs already set up. So what we're doing is an unusual type of device. So we don't have the rules yet, the models of how it would react on certain cryogenic temperature. Cryogenic is those dealing with the absolute zero type of temperatures, the cold ones. And of course, the algorithm development. So as I mentioned, there's already a lot of progress in developing this, but it's still hard. It's still a challenge to really make use of the power of this quantum computer. Not be discussing this, but this is how one of the complex apparatus that we have, the dilution fridge. So just imagine this one is making use of a helium gas. And it's so cold, but it doesn't freeze. So that's the main difference of the fridge that we have, the normal fridge that we have at home with this dilution fridge. So imagine you can't freeze the chip that you're working with, right? So just keep it cold, and that's why we use this dilution fridge. Also, there's some complexity in terms of the actual design. For the first one, this is the normal, the ICs that you see, the integrated circuits that you see. This is what we're used to seeing, the standard package. But now we're dealing with chiplets, and chiplets means small chips and then stacked together either side by side or on top of each other. We can do that. We are also making use of interposer designs as well. Interposer, this is how it looks like. It's like a bunch of metal connectors stacked together per layer. And there's a lot of nodes that needs to be connected. That's why we are taking advantage of this kind of technology. Right? So what's the future of quantum computing? There's a lot. These are just a few of the areas that we can take advantage of. Pharmaceuticals, we can make use of this through simulating making of new drugs, combining molecules. So right now, I think the computer can only model up to 20 molecules or atoms. So how can you make a better drugs with just a couple of molecules to be modeled? Imagine fertilizers. We have a big plants all around the world making fertilizers. But if you come to think of it, nature is doing it for free. So if we have the power to manipulate or optimize those molecules, we can come up with something or new drugs, right? And or even maybe detection of diseases. Like this would sound science fiction, but maybe before, whenever we go to the doctor, maybe it's too late that you already have this kind of disease, either cancer or whatever. But imagine we can detect it ahead by either using our urine or whatever, right? With all those kind of simulations and modeling. Cybersecurity, I mentioned about encryption, decryption, right? So this is what most of the governments are really into, together with the financial modeling. So that's why everyone is in a race, because there's a lot of confidential data that each of the countries have. So imagine going to the wrong hands, right? Material science, we can invent better plastics or even new materials. So optimization maybe for transportation or database searches, we can have that application of knowing the shortest route, what to encounter. Of course, weather forecasting, right? We can tell ahead what is coming, can prepare for it. And there's a lot more. And everyone is looking into the first few batches of this application once the computer is there already. In terms of jobs, there's a lot of jobs. Okay, I listed here, but there's a lot more. But the field is really heavy on mathematics, engineering, physics, coding, and statistics. So we have to prepare for it. And then in terms of opportunity, let me close this one. Just going back, you see here a lot of pictures of the early computers that we have, or milestones that was developed in every 10 years since the 1930s. So going back 1830s, and then 1990s, World Wide Web was there. In the year 2000, there's a lot already developed, but The notable ones would be the use of Wi-Fi and mobile computing. And then, of course, 2020 COVID. No, we have 2020 machine learning and AI. So what I wanted to ponder in this slide is that there's a lot of opportunities. We just don't see it yet, but through the years, it has been proven that we can do as much when the technology and the knowledge is there, right? So the question is, are we ready? Are we ready for that? Are we equipped for those kind of opportunities when it comes? So remember, we are in the early 20,000s comparing to the 1927 Solvay Conference. We are at that stage, 2025. Okay, and then let me close it with these key takeaways. Quantum mechanics offers undeniable, and it's not strange. It's simply how the world truly works. So I want you to take away with this, again, perspective that it's okay, it's not unusual, it is just how things work. And then quantum computer offers vast opportunities, and it's crucial to let's upskill now, right? And there are just as many questions as there are sources to explore quantum mechanics. So I would say, be Mikkel, be like my son, ask a lot of whys and follow your curiosity. So we have the technology now, we have the sources, and I hope that I opened up your mind or made you excited in looking forward and learning more about quantum mechanics and its future applications. So with that, that's it for me. And I want to thank you all for taking this first step to learning about the promises of quantum computing. I give it back to you, Christine.
Thanks, George. That was so informative and really insightful, actually. So thank you so much for that talk. Now, I'm sure there are tons of questions from the crowd, but before I do that, I'd like to ask all those currently attending to quickly sign the attendance sheet below. There should be a link in the Zoom meeting and in the Facebook Live comment section. This will be for your certificate, okay? So we are actually short on time, but we had some cool questions coming in. I think what we can do is we can just email them to George and have him answer it, and we'll post something or get back to the students who asked. But just one question that I wanted to ask, since we have a lot of college students who participated in this session. I guess, George, I wanted to ask you if these young engineers and students were interested in getting into quantum computing, what kind of skills should they be learning now at this point?
All right. So we talked about the basic principles right now, and I think it would take even my office mates, PhDs, research students, took a lot of years really just to absorb and understand the needed concept. So right now, I think the best way or approach to do it is really into learning about coding, right? Soon it will be there. It is already being developed, but as I mentioned a while ago, this field requires a lot of numbers, mathematics, statistics, right, and coding. So I think it's better to invest in we have an open source development kit for quantum. I think IBM developed that. That's Qiskit. You can search on it and start learning from there. I actually plan to do it myself as well. I don't want to be left behind in the future. So yeah, I encourage you to go search for it and invest time. Right?
Yeah, right. It's a new field, so there's just so much open inquiries to be made, right?
Yes, definitely.
All right. Well, thank you so much, George. Due to the time constraint, we can't answer all of the questions, but again, we'll try to get back to you. Thank you to everyone who asked. And so now I apologize to everyone, but George, this has been an incredible session. Before we wrap up, do you have any final thoughts that you want to share with our audience?
Well, maybe just to say thank you and actually congratulations for taking this first step. It's out there. The documents are there, the websites are there, and expect more to come because, as I mentioned in the early stage, we are at the celebrating the quantum year. So there would be a lot of efforts driven by different companies. All you just need to do is be updated, visit their sites. Actually, LinkedIn is good at that. And of course, stay tuned with what Cynix has to offer. Cynix is really good at influencing or disseminating informations like this.
Thank you, George. I especially love the part where you gave us a behind-the-scenes look into what it looked like to, design the quantum hardware. So that was very interesting. So yeah, to everyone watching, we hope this session inspired you to explore the world of quantum computing. And if you enjoyed today's talk, be sure to follow us for updates on future Xpert Insights episodes. So until next time, stay curious, keep learning, and see you at our next webinar. Take care, everyone. Bye, George.
Bye. Thanks. Bye-bye.